So now that we have a sense for simple covalent bonding from Chapter 8, we need to dive a little bit deeper into some bonding and the actual three-dimensional shape of molecules. And we'll start with molecular shapes and note first off that the Lewis structures that we draw on paper are not good representations of the arrangement of the molecules in three-dimensional space. So if I take carbon tetrachloride as an example and draw out its Lewis structure, here we placed one chlorine on each of the four faces of the carbon. And if this was the actual arrangement, we would assume that the bond angles are 90 degrees between adjacent chlorine atoms and 180 degrees in the other plane between opposite chlorine atoms. But in reality, that's not a good representation of this molecule at all. It actually exists in a very three-dimensional structure where the bond angles are 109.5 degrees between any of the carbon-chlorine bonds. And we can represent that here in this ball and stick model, or more commonly, we use these three-dimensional atomic models where the bonds that are drawn out normally are assumed to be in the plane of the screen or plane of the paper. And wedged bonds are assumed to be coming out towards us, and dashed bonds to be going back away from us into the plane. So if Lewis structures are not a good representation for three-dimensional structure, how do we predict or talk about the three-dimensional structure of molecules and their molecular shape? To talk about it, we use this model known as the valence shell electron pair repulsion, or VESPR model. It's commonly mispronounced as VESPR, but it doesn't actually matter that much as long as you remember the central tenets of the model. And the basic concept here is that electron domains repel each other because they contain electrons, which are negatively charged, and like charges repel each other. And so the molecule assumes a geometry with maximal angles between those electron domains. Now, first off, what is an electron domain? How does this apply, and what sense does this make? Well, first off, an electron domain is simply a region in space around the atom you're interested in that holds electron density, or probability of finding an electron. And so that includes lone pairs, single bonds, and multiple bonds as well. So double or triple bonds simply count as one region in space, and so they're one electron domain, even though it's a multiple bond. We can illustrate this by looking at this ozone molecule here. We have three different atoms, all oxygen, and we can assess each atom in a molecule and assign a number of electron domains to it. So if I look at the oxygen all the way on the left, I can say that it has 4 electron domains, one for each of the lone pairs, so that gives it 3, and then it also has a single bond, which counts as a 4th electron domain. So it has 4 electron domains. The central atom, however, only has 3 electron domains. In this case, it has a lone pair and a single bond. Each of those are an electron domain. And then it has a double bond, which also functions simply as 1 electron domain. The final oxygen atom also has 3 electron domains. This time, 2 of them are lone pairs, and the final one is composed of the multiple bond. So then how do I use the VESPR model to predict shapes for molecules and talk about the 3D arrangement? One thing that's helpful to do is to perhaps take out some balloons, blow them up, and treat each balloon as being an electron domain. You can tie them together so that you have a certain number of electron domains around a central point, which we can consider to be the atom. And then look at the shapes that those balloons take relative to each other, because balloons function very similarly to electron domains in this analogy. What we'll see is that in the case where we have only 2 electron domains, so only 2 regions of space, or 2 balloons, they get as far away from each other as possible. And so we end up with 180 degrees between the 2 domains, and we refer to the electron domain geometry as being linear. Now, I emphasize electron domain geometry because in a little bit we will distinguish that from molecular geometry. There is a difference between those two. The electron domain geometry takes into account all of the electron domains that are present. So if we have 3 balloons or 3 electron domains, then they get 120 degrees away from each other within the same plane, and you can do this with balloons to prove this. And so we refer to this as trigonal planar. Planar because it's all in one plane, trigonal because there's 3 points. The bond angles are 120. If we have 4, then the angles are 109.5 between the electron domains, and we refer to this as being tetrahedral geometry. We can extend this to 5 and 6 electron domains. Beyond 6 is not common in any form or fashion. 5 and 6 are actually fairly rare. Most of the time we deal with is 2, 3, or 4. But for 5, we'll have 3 of them align in one plane, and then 2 sit in the vertical plane, one above and one below. Because this looks a little bit like 2 pyramids stacked on top of each other, we refer to this as being trigonal bipyramidal, where the trigonal refers to the number of points in the base of the pyramid, or the plane. Within that plane, the angles are 120, and then between that plane and the upper or downward domain are 90. Lastly, if we have 6 electron domains, all of the bond angles are now just 90 degrees. It doesn't matter how you measure, and this is referred to as an octahedral geometry. Now, I made a distinction between electron domain geometry and molecular geometry. Why did I make that distinction? Well, molecular geometry, also referred to sometimes as the molecular shape, does not count lone pairs. The molecule still has them. They still affect how the electron domains are arranged, but they are not counted when we name the molecular shape or geometry. So what does this look like? Well, let's just start at the early examples. If I have a case where I have only 2 electron domains, I'll make this distinction here where I have bonding domains and non-bonding domains. Bonding domains simply means that the electron domain is a single or a multiple bond. Non-bonding domains, what we're really talking about there is lone pairs. So if I start out with 2 bonding domains, then linear geometry, in this case where I have only 2 electron domains, even if one of those is replaced by a lone pair, if I talk about the shape at all, it's still just linear. So the case where I only have 2 electron domains is fairly simple, but you can see that it starts to get more complicated as I move to 3 electron domains. Here, the electron domain geometry is trigonal planar, and if all of those are bonds, then the molecular geometry is the same, trigonal planar. And this is always the case. If all of the electron domains are bonds, then the molecular geometry is the same as the electron domain geometry. However, if one of these is a lone pair, then we get to a case where if I look at this structure right here for NO2 minus, I don't tend to draw out lone pairs very frequently. And so if I just look at the actual atoms, rather than looking like a trigonal planar geometry, it looks more like it's just kind of like a bent nail. And so we refer to this molecular geometry as being bent, where we're really just looking at the atoms that are present. So you can see we have a molecular geometry now that is different from the electron domain geometry. This is how we would sort of name the molecular shape. As we increase to 4 electron domains, or 5 or 6, the situation gets considerably more complicated. Again, if all of those are bonding regions, then the molecular geometry is the same as the electron domain geometry. However, if one of those regions for tetrahedral, if one of those for 4 electron domains is a lone pair, then what it looks like, we've lost the top part of the tetrahedron, and it looks more like just a 3-sided pyramid. And so we refer to this as being trigonal pyramidal. If we lose 2 of those domains, then it goes back to looking like a bent nail, and we refer to that molecular shape as being bent. So you can see that this begins to get complicated, but if we keep track of the normal system for electron domain geometry and find that first, and then work from that into the subset of the molecular geometry, we should be able to keep track of everything. So let's start with maybe just a couple example problems. So HCN, I'll just go ahead and draw out the Lewis structure, and this is how you want to start these problems. You want to first draw the Lewis structure, which doesn't give you the 3-dimensional shape. Identify your number of electron domains around the central atom, and primarily we will be talking about the central atom for these molecules. and its geometry. And then after you've identified the electron domain geometry, then you can assign the molecular geometry based on the subset of electron domain geometries. So HCN, if I draw this out, HCN, and if I look only at the central atom, so carbon, what I'll notice is that it has only two electron domains, electron domains. They're both bonding. I have a single bond and a triple bond. And so my molecular geometry is going to be the same as the electron domain geometry, and I would simply refer to this as being linear for its molecular geometry and its electron domain geometry. So I'll write EDG for electron domain geometry and MG for molecular geometry. SO3 2-, well, we've seen this one before back in chapter 8. That's single bonds to all the oxygens, a lone pair on the central sulfur, and of course lone pairs around the outer atoms. If I look at this case, the electron domain geometry, well, first, how many electron domains are there? There's a lone pair and 3 bonds, 3 single bonds, so that would be 4 electron domains. So my electron domain geometry will be tetrahedral. However, my molecular geometry does not count the lone pair, and so it looks like I have only 3 things forming the base is a 3-sided pyramid. So this would be a trigonal pyramidal structure. Trigonal pyramidal. Some people use the term trigonal pyramidal. Depends a little bit on your dialect and preference. Finally, let's take a look at Cl2CO. Well, if I draw this out, that's carbon, Cl. Ooh, let me draw this out a little bit differently. Cl, Cl, and double bonded to O. The central atom there is carbon. It has only 3 electron domains. 3 electron domains is a trigonal planar geometry, and the molecular geometry is actually the same because there are no lone pairs on carbon. Finally, NH2- is simply N with 2 lone pairs, H and H. This has 4 electron domains, 2 lone pairs and 2 bonds. So the electron domain geometry is tetrahedral. But the molecular geometry leaves off the 2 lone pairs, and so the system looks more bent. And that's how we would use this for characterizing the electron domain geometry and the molecular geometry, keeping in mind that the point behind doing all of this is to be able to draw these molecules fairly accurately, or at least relatively accurately, in their 3D arrangement in space.